Okay. Thanks, Mona. So if there are any questions about yesterday, let me know, and then we can start. Okay. I see no questions, so we can start doing a brief recap of what we did yesterday. So let me share my screen. I hope you can see it. So yesterday we did an introduction. Sorry, I call it introduction, but the more I see it and the more I don't like it. Let's say a few bullet points about the hydrology that we stressed quite a lot, and we are going to stress also today about the hydrologic cycle. And then we went through the basis of HMS. We went through an introduction about HMS, what is HMS, what is the purpose of HMS, and then we really start with opening the software and trying to, let's say that the main topic of yesterday was, to extract a basin, a sub-basin from our DEM with the use of HMS. Use of HMS that, remember, needs always to be done with the help of a GIS software, in our case, QGIS, for multiple reasons that we have seen yesterday. Now, more or less, we are at point 3, but believe me, the remaining points will be covered all today, because let's say that I think that one of the most important things is the creation of the georeference basin that can be used also for other purposes, as we have seen yesterday, not only for HMS modeling. So today we are really going to build up our model and to run a simulation, an event simulation. And then at the end, we will see really quickly how to calibrate and validate our model, and what we will be able to see during the in-person trainings. So let me move, as we were here. So we were able to open our HMS, upload the DEM, and extract the basin. I hope that at least some of you were able to follow the different steps and were able to extract the basin. And because right now we are going to create the meteorologic component, the control specification, and we will add also the precipitation, that, if you remember, is our main boundary condition that we didn't add yet. So before we start, I have really few words to spend, if we go back to the presentation, about the characteristic of the basin, because HMS gives us the possibility to calculate automatically. So HMS calculates automatically the characteristic of the basin that we have extracted. And this is pretty useful in case we want to do an analysis of the basin that we obtained. And to do that, we just have to go under Parameters menu And there is a characteristic option. Now here I can select only the subbasins characteristic because we decided to use a single, a single catchment. And so we have the calculation of the characteristic of this single catchment. But in case, as we were looking at yesterday, we have multiple catchments with reaches, we will have the possibility also to calculate the reaches characteristic. So just that, so that you have an example. Let me really quickly move the position of my breakpoint so that I can show you. And delineate back again. The catchments and the reaches. Sorry, maybe I did something. I did cancel. Let me see if somebody is waiting. Okay, no. Okay, so let's do an example. If you go on parameters menu characteristic, see that now I have also the reaches, and I can also calculate the characteristic of the reaches, and not only the subbasin. So just by clicking on it, for example, subbasin, HMS will calculate, okay, all the main characteristic of the subbasin, of the catchments, and of the reaches. Let's see some example. We have for the subbasins, for each one of the subbasins that we have the longest flow path length, the longest flow path slope, okay, that can be, for example, assumed as the slope of the main drainage line of the catchment, the centroidal flow path length, the basin, the general basin slope, the basin relief, and a lot of different other characteristics. Now, I don't want to stress you about describing all of these characteristics. You have some examples here in the presentation, in which we explain at least the main characteristic of the catchment that you can have with HMS. But yeah, for example, as we were looking at, there is the average slope of the maximum slope of every cell, the maximum elevation differences of the catchment. And then there are, for example, the elongation ratio, the drainage density, so that is the ratio between the length of the river and the basin area. But I can tell you that usually the most important things are, as you can imagine, the basin slope, the basin relief, and the longest flow path length, and slope, of course. And I will tell you later on why you have to remember this longest flow path length and longest flow path slope. So same things we can do for the calculation of the characteristic of the reach. So just easily clicking on it, you see that in this case the characteristics are only 4, so the length, the slope, the relief, and the sinuosity. Also in this case, I don't want to stress you too much. We can move on pretty quickly. But as you can imagine, the length and the slope and pretty simple. The only characteristic that is maybe a bit complicated, is not quick to have is the sinuosity. Well, the sinuosity just indicates, how much the river lines is not straight, okay, from the beginning to the end of the catchment. Okay, we have a question. In the map layer, there is discretization list. Could you have described more? What you mean with discretization list? Sorry. You can switch on your mic. Microphone, okay. Map layer, let me check discretization list. You mean this list of different layers? Or you mean only discretization? Okay. Yeah, you know, the map layers is not, let's say, it's the GIS component of HMS, okay? So as you do it for QGIS by adding the different layers and watching the different layers on the map, HMS works in the same way as all in the GIS environment. So in this case, what happened in the map layers? The map layers can work in two different ways. So the first one is you can add directly some shapefile, okay, that can be point lines or polygons. The other way in which these map layers works in HMS is whenever the HMS creates something, it will just put it on the map. Okay, so for example, whenever we do the pre-processing of the sinks, so the pre-processing sink field or the pre-processing drainage, what will happen is that HMS will directly create some raster layers that are necessary in order to calculate, for example, the identified stream. So whenever it creates something, it will directly, so for example, a raster layer or a shapefile, it will directly put it in these map layers, so that in case you need it, you can see it directly on the map. Yeah, it is really maybe interesting to see what are all these layers. For example, the 1018 flow path. It is related, to the, if you remember, the longest flow path length, the 1018 flow path is the 85% of the total flow path of a single catchment. So some of them are really complex, some of them probably you will never use it, but HMS will anyway directly put it on the map layers. So what I can tell you is that for the creation of the model, what is really important, as you can imagine, is of course the icons, okay, that then you can select directly both in the on the map or directly here in the top left. The sub-basin, because in that way you can see, and of course the terrain. Okay, remember that HMS, the final purpose of HMS is not really to work as a GIS environment, but is to create a model and run a simulation. For example, I'm just going to give you some historical information if you don't know about HMS. If we consider just, let me admit the remaining people. If I'm not wrong, all this GIS menu has been added into HMS starting from, I think, 2020. Okay. Before 2020, what happened is that you had to use an external software to do exactly the same things that we have done yesterday. Okay. So before 2020, you had to couple two different softwares just to do the extraction of the basin. You could directly create your components, your elements by, and that's why I didn't explain you, but here you have the possibility to add some elements directly manually. So manually you can click on one of these sub-basin creation tool, you can click on the map, and you can create a new sub-basin element. Why this is a bit, let's say, old style? Because, as I was telling you, before 2020, there was not a possibility to work in this GIS environment. So usually what you have to do is to work with an external software and then modify it manually here. But after 2020, after the institution of this GIS menu, everything has been simplified. And so I understand that there are a few things that remains and that are a bit old and let's say maybe not useful, okay, nowadays. But yes, that's why also for the map layers, just to complete my answer, there are a lot of different stuff that probably are not useful to us, but that remained from that pre-2020 version. So I hope I was able to answer you. Okay, well, we were looking at the characteristic of the reach. We have seen the characteristic of the reach, and we can move on with our presentation. We can really start going deep into details of the creation of the model and the parameters, the estimation of the parameters that we need to calculate to do this transformation from inlets to outlets. So let me move back my breakpoint so that I can create again my catchment, and we will directly work on it. Okay, single catchment without any reaches because for a complexity reason. Okay, we only have a couple of days of training, and if we do the model of the entire Atbara subbasin, it would require much more than just a couple of days. So the first things that I want to show you is how and what we need to do for the completion of our model before we run our simulation. If you remember, we talk about three main steps on an hydrological study. The first one was the precipitation analysis, so the analysis of the precipitation pattern. The second one is the identification of the catchment. And the third one is the transformation from inlet, from inflow to outflow. So the transformation from the precipitation, that is our boundary condition, to the effective flow of the basin. If you remember, another point that I stress, another concept that I stress a lot was the answer of the catchment. So what we are missing is we need to know the answer of our catchment, of our Tekeze catchment. And this is the schematization of what we want to do. So we have our boundary condition that we need. So we already did the precipitation analysis. We just have to upload our data into HMS, and I will show you later on how. And then we need to use these two methods, the loss methods and the transform methods, inside HMS. And these two methods are the main ones that you have to use in HMS for the transformation from inflow to outflow, so that the final result of our simulation will be the effective flow. Always remember that right now we want to perform the event simulation and not the continuous simulation. I will show you at the end of today why we didn't have enough time for the development of continuous simulation. But mainly, the main problem is the fact that for a continuous need only to select and prepare the how can I say the methods of the loss methods and the transform methods. Okay, but you need also I think at least other 3-4 other modules, okay, that you need to add in HMS to calculate the effective flow in a continuous simulation. I know that is a bit complex right now, but once I will show you what I mean, it will be much more easy. So right now, for this event simulation, we need to find the perfect method for the calculation of the loss of the precipitation and the method for the calculation of the transformation, okay, from the precipitation into effective flow. So what HMS does is to divide the calculation, so the transformation from inflow to outflow, into two main modules, two main methods. The first one is the loss method, and I'm going to explain you what is the loss method. The loss method calculates how much rain, okay, get lost due to, for example, deep infiltration. So after the loss method, we will have only what is called the effective precipitation. So that portion of the precipitation that will transform into effective flow. And how to calculate how this effective precipitation transform into effective flow with the transform method. So HMS use two different modules for two different calculations. It's a bit complex, but that's how it works. So if we go back, I hope that at least somebody of you was able to arrive at this point of the creation of the basin. In case you were not able, remember that you have, and let me show you, you have directly in the training folder material a project with all the basin already complete. So if you go in the material folder, you will find a folder called AT Takez Training SCS. And if you open it, you will be able to open directly this .hms file. And you will see that is exactly what we are going to do right now. You see that the basin is the same. You see that here you already have the remaining modules that we need to add. But at least you can have a base from which you can see what we are going to do. So if somebody of you was not able to follow step by step what we did yesterday, you can directly open the model that is already pre-made inside the training folder. I will stop here really quickly. and ask if there are some questions. It's a bit complex by explaining directly without showing you what I mean, but I will do in a few moments. But if you have any questions, just let me know. We can stop for a couple of seconds. I see that in the meantime, there are a lot of new participants. So if somebody of you is just joining us and don't know where we are, just let me know so that I can repeat. Kindly unmute Engineer Philip Acol. I think I tried to unmute everybody. So I hope Engineer Acol, you were able to join us. Okay. Okay, I see a hand raised from Engineer Ishag. Please, you can switch on your microphone. Nicola, maybe as we wait, you can do a recap. You mean a recap of what we are going to see today, or a recap of what we did yesterday? Today, sure. So we didn't have the chance to see a lot, but what we did today that we were not able to do yesterday was the calculation of the characteristic of our catchment. Okay, because HMS gives you the possibility to automatically calculate those characteristics. So once you have extracted the basin, you can directly move into parameters menu. There is a characteristic option. Into this characteristic option, if we click on subbasin, HMS will directly be able to calculate, depending on the morphology that we have of our DEM, is directly able to calculate the main characteristic of your subbasins, of your catchments, and of your reaches if you have. Some of these characteristics are, for example, the slope of the basin, the maximum flow path length, and some other characteristics that can be more or less useful depending on what you have to do. And then we move on the real, starting talking of the real creation of the model. So of those components of the hydrological study of transforming the boundary condition, so the precipitation, into the effective flow. So we want to understand and to know the answer of our catchment, the hydrological answer of our catchment. So how, depending on the characteristic of our catchment, the precipitation is transformed into the effective flow. And to do that, HMS uses multiple, they're called modules or methods, for the calculation of this transformation. In particular, today we are going to do an event simulation, so the simulation of a single rainfall event, that, if you remember from yesterday, needs a lot less processes, occurs, okay, because, for example, the evaporation, the transpiration can be neglected in case we are talking of a single event simulation. So in case we are talking about a simulation of few days, and the only methods that we need for the calculation of the catchment answer is the loss method and the transform method. Now, the loss method, what it does? The loss method is used to calculate the part of the precipitation that get lost, and that's why it is called loss method, due to, for example, deep infiltration. At the contrary, the transform method that occurs after the loss is used to calculate how the effective precipitation, that is the remaining part that is not being lost due to infiltration, due to deep infiltration, how this effective precipitation transform into the effective flow. So I think we can stop here. This is the recap. If there are no questions, we can move on. Okay. In case, anyway, stop me. So we're going to see how to
yes,
create...
Nicola, before you
yes.
proceed, if you just quick one, if you wanted to delete the catchment after you delineate the catchments, and because when you delineate the catchment, I think you put the intersection point, and then when you want to delete the catchment, all the catchment, and then you want to work, what are you going to do before we proceed?
You mean
Sorry.
that... Sorry, I hope I understood. You mean, for example, here I have a single catchment, and I want to delete because I want to, for example, move back in the condition in which I want all the different subcatchments of the Atbara. You mean, for example, that?
Yes, for example, if you're working and you make a mistake, I want to delete the catchment and then to delineate from the beginning. What do you want to do? To delete the whole work?
Okay. Yeah, it's clear. So there are two different ways. The simple one is just, to move the breakpoint. For example, I selected this as the location of my breakpoint, and then I see that the layer that I have uploaded as my reference point is the wrong one. Okay. So, for example, I add a new layer for a new reference point, and I see that my breakpoints would have been like, I don't know, 100 kilometers upstream. What I can do is really easily just move my breakpoint on a new location. And delineate back again in the GIS menu my elements. Because if I delineate again, what will happen is that HMS will delete the existing elements, so the catchment that you have created, and will create the new ones. So if we click on delineate, and then here you can select, as always, the prefix, you see that you have a message that says existing basin model elements must be deleted before continuing to delineate new elements. So if we are continuing, the elements will be automatically deleted and will be replaced by the new ones. So if we click continue, the previous one will be deleted and the new one will take place. Another way, I think, let's try, is directly to delete manually. How to do it? You just have to right-click on the selected element, and there is the possibility to rename, or in this case, delete my element. Let's try. You can delete it manually. Here, do you wish to delete hydrological element? Okay. You can delete also the sink in the same way. Do you wish to delete hydrological element? Yes. And then we are in this situation. Okay. So it's the same situation that we have before we delineate the elements. So I can move on back again my breakpoint wherever I want in my new location. And I can go back in GIS menu delineate. And let's see. In this case, we don't have the message of HMS asking us and telling us carefully if you continue, your existing elements will be automatically be deleted, because we have already manually deleted them. And it will directly create the new elements of the basin. Is it clear?
Thank you. Thank you. That is clear. Thank you. Thank you very much.
Perfect. Okay, so we can proceed if there are no other questions, in case, stop me. So this is the real core of simulating in HMS. Is the selection of the method that we are going to use for the calculation of the loss, and the selection of the method that we are going to use for the calculation of the transform. Why I'm saying the selection of the methods? Because if you are already familiar with hydrology in general, you know that there are multiple equations, multiple theoretical studies, multiple ways in which you can calculate the precipitation loss. And there are multiple ways in which you can calculate the transformation from effective precipitation to effective flow. In this case, we are doing an event simulation. So each one of these different methods, okay, depending on the study that has been done, requires different variables, different coefficient. Just to give you an example, the loss method, and we are going to see it really quickly, have multiple possibilities for the calculation. Now, some of them can be used only for the event simulation. Some other can be used only for a continuous simulation. Always because there are a lot of processes, such as the evaporation and so on and so forth, that are not required in an event simulation. So, for example, there could be methods of the loss, of the calculation of the loss, that requires informations about the soil, the infiltration, the land cover, the urbanization of the area, or some other methods that requires only few informations. In this case, what we are going to do for this event simulation is to use the SCS curve number. So it is called the Soil Conservation Service curve number. And this is a method that is one of the most used methods, but that can be used only for the event simulation. Yes, only for the event simulation. Same things for the transform methods. There are multiple ways in which you can calculate how the effective precipitation become flow, effective flow. And the most common one is the Clark unit hydrograph, because it's pretty simple, okay, and requires only few informations about the catchment. So right now we can move to HMS and see how to select the different methods, and how to select the variables and the coefficient that are needed for the calculation of those methods. So let's move into HMS. If you remember, whenever you click and you select an element here on the top, what will happen is that on the bottom, you will have all the information about the element that you have selected. So, for example, if we click on the catchment that we have created, that is called, in my case, S1, okay, let me know if you're able. What will happen is that here you will find a lot of information about my catchment. So let's read, for example. The first information is how my catchment, or with what my catchment is connected downstream. In this case, it's called sink 1, because HMS transforms my breakpoint into a sink, into a tank, from which I can then in the future be able to see the results of my simulation. But here there are a lot of interesting information, such as the area of my catchment. For example, in my case, 29,127 kilometers square. The latitude and the longitude, carefully, because this information, these coordinates are the coordinates of the centroid of my catchment. And then, as you can see, there are a lot of different methods, okay? For example, discretization method, canopy methods, snowmelt methods, surface method, loss method, transform method, and base flow method. All these methods are used for the calculation of the effective flow. Why we see 1, 2, 3, 4, 5, 6, 7 methods instead of 2 methods that you see here in the presentation? Because this one is the maximum possibility that you have for HMS. And as I was telling you, the most complex simulation is the continuous simulation. In the continuous simulation, you need to select all these 7 methods. Each one of these methods is used to calculate. Each one of these methods is used to calculate the answer of the catchment to a determined process. For example, the canopy method is used to calculate how the vegetation interacts in our catchment. The snow method, for example, calculate how the snow transform into water. The surface method calculate how the first layer of soil works in a continuous simulation, and so on and so forth. For an event simulation, what we really need is just the loss method and the transform method. So by default, HMS will select a loss method, a transform method, and, as you can see, a base flow method. What we have to do in our case is to change the method for the loss and the transform, and select none for the base flow method, because we don't need it. Okay, so as I was telling you, there are multiple ways, multiple methods to calculate the loss, multiple methods to calculate the transform of our catchment. So if you click on the selection of the different methods, as you can see, there are, I don't know, maybe there are like 15 different methods that you can select for the loss. And if I'm not wrong, like 9 different methods for the transform. So what we need to do is to select for the loss method SCS curve number. Careful, because there is also the possibility to select a gridded SCS curve number. But we need just this simple SCS curve number. You see that whenever you change your method, HMS asks you if you are sure you want to change the methods. In this case, yes, I am. And by default, HMS will select the Clark unit hydrograph. That is exactly what we are going to use for our calculation. I will stop for a moment. and please give me some feedback if everything was clear and if you were able to find all these informations, because sometimes it's a bit tricky. I will wait a few seconds. Okay, I don't see any questions. Now let's move back really quickly to the presentation. Now, as you can imagine, for each one of these methods, okay, that HMS is using, as I was telling you, you need to decide some initial parameters. So some we can call it variables, some coefficient that we select to characterize our catchment, and that will be used to HMS to do the transformation from precipitation to effective flow. Each one of these multiple methods that we can select requires different informations, different coefficient. In our case, after we have selected the SCS curve number, you see that here we have, sorry, let me switch on to the black mouse. That you can see better at least. Okay. I hope it is more visible right now. You see that here on the top, there are a few, there is a small menu, and there is a single menu for each one of the methods that we have selected. So for example, in this case, we have the loss method selected and the transform method selected. So we only have the menu for the loss and the transform. But let's do another example. In case we wanted to do a continuous simulation, let's select casually a few methods. You see that right now, you don't have only loss and transform, but you have also the other methods that you have selected. And you see that for each one of these methods, you need to add some values, some coefficient for different information of the catchment. Let me switch off all these methods that we don't need. And so if we click on the loss, what HMS requires us is to give him information about few coefficient. It is called, the method that we are using, it is called Soil Conservation Service curve number. And it is called in this way because one of the information that we need to give to HMS is the curve number. What is the curve number? And I'm going to explain you why I didn't want to be so, I didn't want to do, let's say, a presentation that is too theoretical. But the main reason is that you can find everything, if you remember yesterday, on the web page of HMS. And in particular, you can find all the information you need in the user's manual. So if you remember in the presentation yesterday, I show you. Let me move back really quickly. Okay. I show you this slide. And if I remember, I told you I don't want to be too theoretically because there is the user's manual. Well, the fact is that in the user manuals, that is really well done. You can inquire directly and see, for example, if you are alone and you don't know how all these different methods work, you can go on sub-basin element. And for example, I wanted to know how all these loss methods that I can select work. So if we go on selecting a loss method, you see that here everything is well explained. Okay, so for example, here we can read from this general information. Let me see. While a sub-basin element conceptually represents infiltration, surface runoff, and subsurface process interacting together, the actual infiltration calculations are performed by a loss method. So how the loss method only calculates, as I was telling you, what is the part of the precipitation that get lost due to the deep infiltration. And here you also have a table really useful. These are all the loss methods that you can select. And as I told you, some of them can be used for the event simulation. Some of them can be used only for the continuous simulation. Okay, so I know that I want to use the SCS model, loss method, sorry. And so I scroll down until you see there is the description of each one of the method that you can use. So I scroll down until I find my, let me find it, okay, until I find my SCS curve number loss. Now here you have a brief explanation of the method that has been implemented in 2007, but in reality, so this is a modification of the original one that was implemented, I think, in 1972, something like that, and can be used only for event simulations. So, as you can imagine, for each one of these methods that you can select, this user manual described also the different component, the different coefficient that you need to add for the calculation. So, for example, for the SCS curve number, what we need is the initial abstraction, the curve number, and the percentage of impervious. What is the initial abstraction and what is the curve number? It is explained right here. So, for example, the initial abstraction defines the amount of precipitation that must fall before we have surface runoff. And what is the curve number? The curve number is represents all of the different soil group and land use combination of the subbasin. So it is, let's say, a combination between infiltration and land use of our catchment that we have in our catchment. I see a hand raised from Muktaba, so please let me know.
What if I have a basin that is big enough that it has multiple curve numbers? As you said, because the curve number is a combination between land use and the soil type, or the the hydraulic soil groups. So let's say I have 86, 79, 91, for example, as curve numbers. Which number? I see that it's only a single input. So how will I deal with this issue? I hope my voice is clear. Okay.
Yes, it's absolutely clear, and it's a really good question.
Okay, thank you.
You're welcome. This is a really good question. So we can, there are, let's say, my answer, it will be a combination of answers. So what you mean is, let's do this example. We have this catchment, okay? Now this catchment, if we go back to the characteristic of the basin, is like 30,000 kilometers square big. So it's really an important catchment. And as our colleague was suggesting, for example, you see that we are in a mountainous area, but for sure, the land use that we have, for example, alongside the drainage line is different from the land use that we have on the edges of the basin. But not only the land use, for example, also the infiltration is different, because here, maybe we are on a, here in the top, we are in a mountainous area, so we can have a soil that is much more impermeable. We could have like limestone or something like that. While here, on the valley, maybe our material is more alluvial. So we are talking about sand, silt, with a different infiltration. So we have a problem of both infiltration and land use. How to select a good curve number? So remember that what we want to do, our final purpose, is to create a model. And what I mean with creation of a model, what does it mean? It means the creation of something that is a good representation of the reality. One really important point about simulation, about modeling, is the fact that you will never, if you are talking about complex system like this one, you will never be able to perfectly represent reality. So we can be more or less precise in the representation of the reality, but always remember that the more accurate we are, okay, the more time and resources we need to spend to create a better model. And what I mean is, we are in this situation, we have different land use and different infiltration. What we could do is to be more accurate in the creation of the catchments. So we could divide these catchments, go back to the identification of the streams, be more accurate by reducing the threshold, and divide this catchment into a lot of different sub-catchments. Now, when we have multiple sub-catchments, what we can do is to assign a different curve number for all these different sub-catchments. So, for example, we could have a sub-catchment like here that we can say, okay, we can apply this curve number for this area, for this sub-catchment. We can have another sub-catchment here, and we can apply a different curve number, and so on and so forth. But somebody else of you could come in and say, okay, but I know this area, and I know that if I zoom in, I have this area that has a different land use. Here, for example, we could have a city. While on this side, I have nothing. I have only hard rocks, and so the land use is different, and the infiltration is different from the other side. What can we do? We can go back to the identified stream, be more precise, and divide this sub-catchment into multiple sub-catchments. The problem is that, as you can understand, the resources that you need to do that is much more different than what you need if you are going to use a single sub-catchment, a single catchment. Because modelings mean representing reality. But representing reality means you will never be able to perfectly, anyway, represent the reality itself. So you need to try to understand the pros and cons of being more or less precise in your analysis, in your study. In case we have overcome this problem of being more or less precise, your question could be, okay, so we are in this situation, we understand that we don't have enough resources to be more precise, and but how do we understand what is the real curve number that we need to use? Well, ideally, what we have to select is a curve number that is a combination, an average value of the different areas, the different land use and infiltration that we have all along this catchment. So what we could do, for example, if we would have a raster layer of the infiltration of the area, we could calculate an average value of infiltration. And for example, if we have a raster of the land use, we could calculate an average value for the land use. This is an example. And at the end of the day, we can, let's say, select a curve number. The final, let's say, part of my answer is always remember that our final purpose is to try to represent the reality. So in this case, in the hydrological modeling, there are so many processes that takes that happen alongside this catchment, in this catchment, that if I wanted to be really precise, also the curve number cannot represent it. So at the end of the day, I can have an initial estimation of the parameter. As I was telling you, for example, if I have a raster layer of the infiltration, a raster layer of the land use. But then what is really, really important, and we can go back to the presentation, is the fact that after we have created our model and we have run our simulation, we need to do a calibration and validation. What does it mean? My final purpose of the modeling is to represent the reality. It means that even if I am using a value of the parameter, a value of my curve number that is not correct, theoretically speaking, okay, that is not really representative of the reality. But if at the end of the day, my model is able with those, let's call it wrong value, to represent the reality, what I have to do is to select that wrong value. I don't know, I know that it's a bit, how can I say, out of the easy way of thinking, but remember always our final purpose, to represent the reality. So if I can do all my studies, of all my field survey to understand the infiltration values of my catchment, to understand the land use of my catchment, and after I have done all my studies, I understand that I need to use those specific curve number, and I run my simulation. But during the calibration, and what I mean with calibration, well, we will see it later, but just a few words. With calibration, I mean compare the result of my model with the values, the observed, for example, the observed flow stations. And I see that my results are different, are much different from the observed values. I need to change my curve number. I need to change my parameters until I find a result that is, let's call it similar to the observed data. Okay, so I don't know if I was being able to answer to your question. That's a good question, and it is really important because right now we are talking about the initial estimation of the parameters. But yeah, the important thing is that the initial estimation of the parameter, it is called initial estimation and not final estimation, because after the initial estimation and the running of the simulation, the final value will be the one that better represents the reality. So that give us results that are more similar to the observed data. I hope I was being able to answer you. So we can proceed if there are no other questions. Here in the presentation, you have also the mathematical equation of how the loss and the effective precipitation is calculated with the SCS curve number. And if we are talking about, as we were before, about the initial estimation of the curve number, the following slide gives you an idea of what the curve number is for the ones of you who is not familiar. Well, the curve number is a dimensionless number that has a range that goes from 0 to 100. And it is related, as we were saying, to the soil type, the infiltration, the land use, and the depth of the seasonal high water table. So depends on a lot of different variables, and consider the fact that there are all these variables, but at the end of the day, what we have is like three different tables with a total of less than 100 values. Now here you have a table that we can use. Where did I find it? Really easily. I just Googled, and you can do the same. Runoff curve number, and there is a really well done Wikipedia page that described the methods, but not only describe the methods, but gives you information also on how to select the coefficient based on infiltration and land use mainly. So, for example, if we read a bit on this page, I hope you can see it. You see that first of all, the selection of curve number is divided into 4 groups. Now, these groups depend mainly, okay, on the infiltration rate. So we have group A, B, C, and D, depending on the infiltration. Group A has high infiltration rate, group D has low infiltration rates. The other things is the land use. So depending on the environment in which we are, okay, for example, here we have a fully developed urban areas. We have a table with different land use possibilities. So, for example, if we look at the fully developed urban areas, we have open spaces, impervious areas, streets and routes, urban districts, and so on and so forth. If we scroll down and we have cultivated agricultural lands, we can have different curve number for different land use, such as the fallow, the row crops, small grains, and so on and so forth. And we can scroll down until we find also arid and semi-arid rangelands. That in our case, if we, I don't have the QGIS open here, but if we look at the satellite image, this could be a good example. Also in this case, for the arid and semi-arid rangelands, we have different cover types that we can consider, for example, herbaceous, oak aspen, pinyon juniper, and so on, until we arrive to the desert shrubs. Now, not only you have different values for the infiltration, the environment, the environment and the cover type, but you have a different value also for the hydrologic condition for each one of the cover type. Now, the hydrologic condition here is divided into poor, fair, and good. Means everything or nothing, because it's not easy to understand what is poor, fair, or good. But what we can say is that, for example, good is like good precipitation rates, while poor is, for example, if we are in the desert shrub, in a poor condition, we can assume that the precipitation, the mean annual precipitation could be, I don't know, less than 200 millimeters, something like that. So once we have done our analysis, that could be done by remote sensing, could be done by surveys like geophysical surveys, soil surveys, and so on and so forth, we need to decide an initial parameter. Why I'm not too scared about deciding the initial parameters? Because once we have decided the initial parameters, always remember that we have to run the simulation and do the verification of our initial parameters. It means that until the results are not similar to the observed data, we need to change them. Okay? Let me stop here for a few seconds, but I think it was easy, also because you all have backgrounds about hydrology in general and modeling. So I can wait 2 seconds in case you have any questions, and then we can proceed with the selection of a curve number value, and we can proceed also with the transform method. Okay, I don't see any hand raised. Now, as I was telling you, I'm not too scared about the initial decision about the parameters. Of course, what it would be good is to do at least a remote sensing analysis, and at least also, if you have the possibility, some soil survey. But we can select a value for the moment. So let's consider we are in an arid and semi-arid rangelands with a cover type of, I don't know, desert shrubs, because we are quite in a desert maybe environment. There is not a lot of urbanization in this case, but we have good hydrological conditions, because in this case probably I don't know exactly the precipitation. We can check, but let's assume an infiltration rate that is an average infiltration rate. So we can get a value of almost 80. Why 80, not 79 or 78 or 76? Because I am just doing an initial estimation of the parameter. Now, I don't have a lot of information about the catchment, but we can assume, for example, an initial estimation of a curve number of 80. So let's select 80, for example, and then we will see together, after we run the simulation, how the change of this parameter can influence our result. Now, what we need to select is a value for the initial abstraction and a value for the impervious. Let's start with the easy one, the impervious. You will have more or less always the impervious in whatever methods you're going to use. And is the percentage of the area that cannot absorb water from the precipitation. For example, because if we are on an urban environment, we know that we have like, I don't know, 70% that is composed by, I don't know, streets, buildings that are absolutely impermeable. So in that case, I just have to change the percentage of impervious here. And the percentage of the area of my subcatchment, of my catchment, will not infiltrate water. In this case, we are not in an urban area, so we can keep the impervious as 0. We need to select a value for the initial abstraction. Now, if we go back on the user manual and we read, you have some information about it. First of all, the first things that HMS tells you is that, sorry, let me zoom a bit so that you can see better. Okay. The first information that HMS gives me is that you may optionally enter an initial abstraction. You may optionally. Why may optionally? Because, let me check, if this value is left blank, it will be automatically calculated as 0.2 times the potential retention, which is a value calculated depending on the curve number that we have selected. So if we leave the initial abstraction blank, it will be automatically calculated. Now, here in the previous slide, you have the mathematical equation, and you see that the initial abstraction is 0.2 times the variable called S, that is the potential maximum soil moisture retention. That is exactly what we were reading from the user manual. So let's start our model by leaving the initial abstraction blanks. And then it will be automatically calculated by HMS. So we have selected the values for the loss method. So for that method that will calculate all the part of the precipitation that will be lost, what we are missing right now is the transform method coefficients. Also in this case, the transform method's coefficient can be visualized, what we need, here on the user manual. Instead of selecting a loss method, we can click on selecting a transform method. If it works, yes. Also in this case, there is a really good explanation. And also in this case, you have an explanation of how, in our case, the Clark unit hydrograph transform works. Not only of how it works, but also of what are the coefficients that we need to select. So for example, for this method, it's really easy. What we need is just a couple of coefficient. The first one is the time of concentration, that is the most important, and the second one is the storage coefficient. The time of concentration is the most important because what is the time of concentration? It is the maximum travel time of the catchment. What I mean is the fact that the time of concentration is the time that a raindrop needs in case it is it fall in the most far away point of the catchment, is the time that that raindrop needs to arrive at our breakpoint. Okay, I don't know if it is clear, but it's the maximum time that a raindrop needs for reaching our breakpoint. So as you can imagine, how to select the time of concentration, we need to consider a mathematical equation. What is the time of concentration depending on? As you can imagine, it depends on the morphology of the catchment. So let me stop here for a few seconds if you have any questions. This is the most probably complex part of the training, and is, well, as we were saying, is the selection of the different methods and the selection of the coefficients that are needed for the different methods. So it is the more complex part of the training. So we'll stop for a few seconds so that you can elaborate it and let me know if you have any questions. Okay. I don't see any questions, so we can proceed. I hope it is not too boring. Now, as I was telling you, for the initial estimation of the time of concentration, there are a lot of different formulas, okay? Mathematical formulas. One of the mathematical formulas that we can use is the Giandotti formula. Why we can use it? Because the Giandotti formula has been done for catchments that has an area that is bigger than 170 kilometers square. What I mean with has been done, all the formulas that you can use for the calculation of the time of concentration are not theoretical formulas, but are formulas that derive from experiments, okay? And so, in this case, Giandotti, okay, did the calculation, the experiment, only for subbasins that were bigger than 170 kilometers square. That's why there is this range. How does this formula works? It is dependent, as I was telling you, it is dependent to the morphology of the catchment, and in particular, it is dependent from the dimension of the catchment. It is dependent from the length of the main streamline. So if you remember, while we were doing the characteristic of the basin, if you remember the longest flow path length, and it is dependent on the average elevation of the basin and the elevation of the outlet, that is, as you can imagine, the lower elevation of the basin. So it is dependent from the dimension, elevation, and streamline length of the catchment. All of these characteristic, if you remember, has been automatically calculated from HMS. So to calculate the time of concentration, there are two possible ways. The first one is to, for example, do it on paper. Okay, we have the values of the area of our basin, the values of the length of the streamline, we have the values of the average elevation and the lower elevation. And we can do it manually, or we can use the calculator. What is the calculator? HMS gives us the possibility to use a tool, okay, that directly works with as a calculator. The good things is that not only it works as a calculator, but can use the variables that has been calculated directly from HMS. So with this calculator, we can directly use the characteristic of the basin that has been calculated, such as, for example, the dimension of the basin, the longest flow path length, and so on and so forth. And it means that we can calculate this time of concentration automatically. And this is a good help. Now, brief of history of HMS, this calculator has been added in, I think, 2021, 2022. So it's something that is pretty new. But it's exactly what we need right now. So how does the calculator works? If we go back in HMS, you have the parameters menu. In the parameters menu, you see that you have a lot of possibilities. And if you remember, discretization, canopy, surface, loss, transform, and so on and so forth. These are all the methods that you can select for the calculation of the answer of your catchment. In our cases, we are using only two of these methods, and are the loss method and the transform method. Now, I'm going to show you how it works, but it's really simple. For example, if we select the loss method, here we have our SCS curve number that we have selected for our catchment. And here you have exactly the same table that we are looking at in this section. So we have two possibilities. We can change the values from here, as we did before, or we can change the values from here. What is the difference? There are no differences, but from this window, we can use the calculator. So if we move to the parameters menu, transform method, Clark unit hydrograph, this is exactly the same table that we see here, from which we can change the variables, okay, of our transform method. But on this window, we have the possibility to use the calculator and to automatically calculate the time of concentration. Okay, so let's try to do it. We open the calculator. You see, here you need to select the field, the variable that you want to calculate. In this case, the time of concentration. And here, if we go on stats, you see that here you have all the characteristic of the basin that has been calculated automatically by HMS. So in the bottom, we just need to copy-paste the equation that needs to be used for the calculation for the estimation of the time of concentration. So I don't know if I have it here in the presentation, but in case I can copy-paste the equation on the chat of the meeting, okay? Because I have it here, I've used a few days ago. So the equation that we are going to use is exactly the one that I have shared with you in the chat. Well, why it is really useful? Because, you know, if we have the calculator and we already have the equation, we just have to copy paste the equation, and we can directly automatically estimate the time of concentration of our catchment. So as you can see, the estimation of the time of concentration depends on the area of the catchment, on the longest flow path length, and on the basin relief. The basin relief, if you remember, is the difference in elevation between the highest point of our catchment and the lowest point of our catchment. And if we click on calculate, HMS directly and automatically calculate the time of concentration. I will stop here. This is the most tricky part of the training. The calculator is something that you will see probably also in QGIS in a more advanced training. But it is important to know that it is there and can be used, and can be really, really useful. Can save a lot of time. Okay. Let me stop here for a few seconds. If it is possible, let me know if you are able to follow the instruction and to do what I am doing right now on my laptop, because it would be nice if you are able to build by yourself the model. So if you can give me some feedbacks, if you have some screenshots, it would be nice. And remember, for the ones of you that were not able to follow the instruction, you can open directly the model that has been pre-made in the training folder material. So let's wait a few seconds. Okay, Manuel, we have a good example. Okay. I think we can proceed. Yeah, as I was telling you, it's the most tricky part. But once we are going to do a sort of calibration, you will understand that how this coefficient change the result of our simulation. So right now, we have estimated the time of concentration. What we are missing is the storage coefficient. So back again, I don't want to be too theoretical. If we go back to the usual manual, we have the description of the storage coefficient. Also, in this case, it's a dimensionless value, so it's a dimensional ratio, and can be defined as the storage coefficient divided by the sum of the time of concentration. Can be defined by dividing the sum of the time of concentration and the storage coefficient. So it's just a dimensionless coefficient. As a first estimate, we can use the same value that we have for the time of concentration. So for example, in my case, I have 35.8 hours of time of concentration. I can select 35.8 also for the storage coefficient. Why I am not worried about selecting these values? Because the time of concentration is something that I have calculated and is dependent on the basin characteristic, morphology. And always remember that we are doing just the initial estimation of the parameters. Parameters that will be changed and modified during the calibration. So I see hand raised from Dr. Neil. Oh, okay. I see that you have a screenshot also. Yes, Dr. Nade. If you have any questions, I see that you have also done the time of concentration calculation, so it's nice. Otherwise, we can proceed. Okay, I see that also Liebo was able. Really good. So we are just doing an initial estimation of the parameters that will be changed once we are going to do the calibration. So we have selected, yes,
Hey.
Muna.
Oh, there's no that. There's no.
Okay, maybe.
So, I'm sorry.
Yes. Okay. Just a problem of the microphone. Okay, so we have done this initial estimation. You could ask me, okay, we have set the time of concentration, we have set the storage coefficient, but we have also other option here for the transform. Yes, that's true. We have the option of the different methods and the option of the time area. What are these? These are different way in which the transform Clark method can calculate, in which the Clark unit method calculate the transformation from effective precipitation to effective flow. In this case, we are just trying to do the most easier method. So it's fine if we select a standard method for the calculation and a default method for the time area calculation. So remember to save. And right now we set the parameters for both the loss method and the transform method. We have 10 minutes left before the break. So we can go back to the presentation and start talking about the shared data. What are the shared data? Remember that we are missing one important component. We didn't add yet to the model the precipitation values. The precipitation values that are our main boundary condition. So I showed you yesterday that in the training material folder, you have also a DSS file. This DSS file, if we open it, is composed by all the precipitations that we used for the Atbara subbasin, and in particular, all the precipitation that we used for the different catchments that we created in the model of the Atbara subbasin. So right now, if you remember, we are trying to simulate an event simulation of the Tekeze catchment. the Atbara subbasin. So what we need to add to the model is this precise DSS dataset that if we plot, I think you all know how to do it. You have done the training, but you just have to select your precipitation data, your precipitation row, and click on the plot button. Okay, if you select it and you plot it, you see that you have the data, daily data of precipitation, starting from 1970 until 2024. Let's try to zoom in to see how 1 year of precipitation is composed. You can zoom in a single year that you like. Okay, you see the year 2020, the year 2000 starts in January, and this is the precipitation that occurs in the average precipitation that occurs in the Takheze catchment during the year 2000. Okay, so this is the data set of the precipitation that we have and that we can use. How to, well, before I show you how to add the precipitation into the HMS, we can talk really quickly about, in general, about the shared data and the type of shared data. So right now we are doing an event simulation, so we are not considering, for example, the evaporation or the transpiration, but the shared data are all those data sets that can be useful for the calculation of, for example, the transpiration of the evaporation, such as the, for example, temperature, the wind speed, the radiation, okay, the air pressure, the humidity. So all these data sets can be uploaded into HMS that, for example, for a more complex simulation, can be used for the calculation of different processes that occurs into an hydrological cycle. So just to give you an example, in the simulation, in the continuous simulation that we performed in the project, we added also not only the precipitation, but also the temperature, because we had information also about the temperature. And as you know, the temperatures influence, for example, the evaporation. The temperature influence the transpiration. So the more data you have, the more you can be precise in the calculation of all those processes that take place during throughout the hydrological cycle of our catchment. In our case, we are doing an event simulation, so what we need is just the precipitation. Now, how to add the precipitation into our HMS model? If you remember, when we start creating our model, what we did is we add a new component. So we added the basin model, we added the terrain data, and what we are missing to complete our model is the meteorologic model, the control specification, and at least the time series data. In particular, the precipitation can be uploaded selecting the time series data. The time series data gives you the possibility to upload into the model data set like the precipitation, the temperature, the radiation, the wind speed. So all these information that can be useful for the calculation of the processes. In our case, we want to add the precipitation. And so just selecting the data type precipitation gauges, we can click on new so that we can create a new time series data. We need, as always, to select a name and a description if you like. Once we have done it, we can create, and you see that right now here, we have a new folder called time series data. If we open it, we have the precipitation gauges, in this case, because it's the only things that we have added, and we have the gauge 1 of the precipitation. Now we can stop here for now, we can have the break, and then we see how to upload that specific precipitation for the Takezze catchment. And after that, we will show how to add the remaining components and to run the simulation. Okay, I think in 2 hours we will have enough time, because the most complex thing was to understand the methods for the calculation of the loss and the transformation. Okay, so I can stop here for now. Let's wait maybe a few seconds if you have any questions, and then we can have the break. Muna, if I'm not wrong, also for today, we are going to do half an hour of break instead of 1 hour.
Yes, Nicola, it is 1/2 an hour break.
Okay. And so then in half an hour we will be back. But
Yeah.
if you have any questions, let me know.
Half hour is not enough.
Yes, we know, but because of the situation of the Sudanese, they said that because of the national exam in country, and maybe they are suffering from the internet shortages. That is why we will take this half an hour only today, but for the rest of the training session will be the same as previous one hour. So it is only yesterday and today for the reason of Sudanese exam.
Okay.
Okay, thank you so much.
Okay, that's great. So we can stop here, and we will be back in half an hour. Okay, thank you.
Thank you.